All right, thanks for coming this morning, everyone. Our first speaker is coming to us from the University of Oxford. This is Ambrose Yim, and he's going to talk to us today about graph filtrations with spectral wavelet signatures. So Ambrose, I'm going to turn it over to you. Take it away.
Good morning, everyone. So I hope you could all hear me clearly. It's 5 p.m. where I'm at, over across the pond in Oxford, and I'm part of this TDA Centre at the University of Oxford, and I'm also part of the industrial mathematics group as well. So today I'm going to talk about a situation where, suppose you have a data set where you have a collection of graphs, and you want to do some data science with them, and can persistent homology help with that task? So let's say we have a data set of finite undirected simplicial graphs, so nothing, no self loops, no double edges, and so on. And what are the data science problems that you might want to do? Well, you might want to cluster graphs, so group similar graphs into clusters, and that might give some insight into this data set. You might want to learn how to classify these graphs. For example, these graphs might be molecules that might function in a certain way, and you might want to, given their molecular structure as a graph, classify and sort of try and infer their molecular function. So this is in the realm of graph classification. And to do data science, I mean, you need several ingredients. So first of all, if you want to do clustering, you might want a distance or a notion of similarity between graphs, but that tends to be difficult. So, a graph at distances and that sort of thing is hard to compute, and whether that corresponds to some, whether that's a good metric for a data science problem is unclear. Or maybe you want something that's even better. You want something that takes a graph and sends it to a vector in Hilbert space. And once you're in Hilbert space, you could just apply your standard machine learning stuff. You know what you can do to vectors in Hilbert spaces, where you could take inner products and measure distances. So can persistent homology come in and try and help us with some of those problems? Well, if, let's say, for each graph we do have a filter function, then we have a map from this pair of graph and filters to the space of persistence diagrams. And we have well-defined metrics on the space of persistence diagrams. And additional to that, we could also take diagrams and map those to vectors in the Hilbert space. For example, you have persistence landscapes as a diagram to vector map. You have persistence images, and those are widely applied in different data science situations with persistent homology. So, I mean, the really thorny question is, what if your data set, in your data set, your graphs are just naked graphs, they're not paired with a filter function? There's no additional numbers attached to your vertices or edges. Then this, you stumble and you can't filter your graphs. Or you do have some data attached to graphs, but that might not be suitable data where you could do filtrations. For example, going back to the example of molecules, you might know the atoms, but you can't order. There's no ordering on carbon or oxygen or nitrogen atoms, and you simply can't filter graphs with that sort of data. And additionally, you might have data attached to graphs, and you might be able to do filtrations, but they might not be insightful. So what we want to do today is to come up with a recipe for writing down filter functions for any graph. And we want to show that we can adapt this recipe, and this recipe can be optimized to different data science problems and to different data sets. And since I am the first talk in this series, I might have a short review of what persistent homology is. And in this case, when we talk about persistent homology of graphs, I want to use a special version of persistent homology called extended persistence. So here we're considering if we have a function from vertices to real numbers, we have subgraphs induced by sublevel sets of the vertices. And we also have superlevel sets of the vertices and subgraphs induced by that. So that's denoted by the lower script and the subscript. The lower script G, lower script T is the sublevel sets, and the G superscript S is the superlevel sets. And so the extended persistence of G along this filtration is this following sequence of vector spaces, where in the first row we have ordinary persistent homology, where we just filter upwards along sublevel sets. But no, we then attach an extra bit where we take the relative homology from superlevel sets downwards. And when you reach the end, you take the relative homology of the whole graph with respect to itself, and that is a zero vector space. And as you know, if we have this sequence of vector spaces, there is an interval decomposition into a barcode, and we record birth and death events of P cycles in this filtration. So if you've never seen extended persistence or even persistence before, I mean, here is a cartoon, basically. So on the left-hand side, we get this cartoon of this graph, and you imagine yourself here as a fish, and you're seeing things under the water level. And the left-hand side picture, you see the water level slowly rising, and that's the ordinary persistence. But in extended persistence, the water level then comes down, and stuff, you could imagine stuff above the water level being fused. So what this does is, you could see ordinary persistence only captures the downforks, the mergers of the sublevel sets, but they don't capture the sort of upforks. And what extended persistence gives is that it captures the upfork information, and ordinary persistence only shows you loops that persist forever. But extended persistence, this construction shows us the full extent, and these loops do die, and then we capture kind of the length of these loops along the filtration. So let's talk about how, given this extended persistence, and we know how to map graphs to persistence diagrams, how we equip graphs with filters. So the real challenge is, we've got this map from pairs of graphs and filter functions to diagrams. How do we construct a pairing if we only see a naked graph? And we want this construction to be sufficiently general such that this works for any graph. So an obvious thing to overcome is, if difficulty is, your graphs in your dataset might have different number of vertices and different number of edges. And we want to filter graphs in a consistent way such that, if we say there's a certain distance between the persistence diagrams, that somehow reflects a notion of similarity between those graphs. I mean, this is a hard question. This is I don't think there's a very clear solution to this, and we're not claiming that we have a solution to this, but this is an ideal that we do want to aim for. And the third point is, we do want to find ways to optimize these filter such that they're optimized and adapted to whatever data science problem we want to solve and our particular data set. So there's several current ways to do this in literature. So there are fixed things you could compute given a graph. You could compute these things on vertices, these numbers of vertices, and you could filter these graphs by those numbers. So for example, the heat kernel signature is used in a recent paper called PersLay to do exactly graph classification, where they filter graphs with this heat kernel signature. There's another recent paper, where they have some discrete version of rigid curvature. They define on vertices, and then they filter graphs by increasing order of their curvature. However, I mean, these tend to be custom things, and who's to say that curvature is the right thing, is the right function to review the underlying structure of the graph. And it seems to work successfully for many data sets, but well, we want something that we can customize and play around with. So another approach is to use graph neural networks, where if you've never seen a graph neural network before, it's basically you have a message passing scheme where vectors are passed between adjacent nodes on your graph along the edges. And you keep on doing this message passing, and you truncate at some epoch, and you take those take the vectors at the nodes, at each node, as your features, and then you filter along those features. But since this is a dynamical system, and these dynamical systems are dependent on how you initialize your dynamical system, so you have to give them some auxiliary data to initialize your graph neural network. And so this kind of, we fall back to the same problem of how do we generate numbers on vertices in the first place. And what we try to do here is we try to bridge the two current paradigms. So we have something that that does not need an initialization, but also has a bunch of parameters that we could play around with. And our paradigm is a generalization of the heat kernel signature used in the PersLay paper. And in fact, this heat kernel signature, as an aside, has been used to analyze discrete triangulations of manifolds and so on. So the generalization of the heat kernel signature is the spectral wavelet signature. And this is a construction using a Laplacian, a graph Laplacian. And in this case, we use a normalized Laplacian, mainly because of the fact that the eigenvalues of the normalized version of a Laplacian fall between 0 and 2. And that makes numerics on that a lot easier. So if you've never seen the normalized Laplacian, it's just like a friend Laplacian, except instead of the degree matrix minus the adjacency matrix, it's the identity minus a normalized adjacency matrix, where the entries in your normalized adjacency matrix is, for each edge, is normalized by the square root of the degrees of nodes attached. And given this normalized Laplacian, I mean, how many things can we do to a Laplacian? Well, we look at its eigenvectors and eigenvalues, and we consider this function on vertices. So we take phi I, the eigenvectors, and we do an element y square. Then we multiply phi I with a function g of the eigenvalues lambda I, and we sum over this weighted sum. And this g lambda is something that we can customize. And yeah, there's some obvious questions that you might ask, why g of lambda, why do we square the eigenvectors instead of, why do we, instead of taking just the raw eigenvector? Well, the eigenvectors, are, even if they're not degenerate, you have a choice of a sign. So when you filter things, the choice of sign is important here. And moreover, if you do have degenerate eigenvectors, and this actually happens surprisingly often in data sets where you've got fairly nice graphs in molecular structures, tend to have nice symmetries, and you get degeneracies in your eigenspaces. And so if you just take your naked unsquared eigenvector and just do a sum of that, that is not unique up to choice of how you diagonalize your matrices. But squaring those, turns out this construction does not depend on your choice of bases in your degenerate eigenspace. Because you could show that if you treat your G as a matrix function, you could just hit it and then hit on L on your Laplacian, and then just take the diagonal entries of that, and that is your spectral wavelet signature that you could assign to your vertices. So how do we parameterize G? Well, any continuous function on a closed interval can be approximated arbitrarily well by a polynomial. So we restrict G to be a polynomial, and if you do numerical analyses, you know that a good basis on polynomial space is our Chebyshev polynomials. And so we take your G of X to be a linear combination of these Chebyshev polynomials, which satisfy this relation. And so the parameters we want to learn, we want to tweak, and we want to play around with are precisely the coefficients in this linear combination. So zooming out, and we go back to this bigger picture. Now we have a map from the space of graphs, and we have a parameter space R of n, which are the coefficients of your filtration, of your heat, of your spectral wavelet signature. And we have a map from graphs to diagrams given a certain parameterization of your spectral wavelet signature. So, I mean, what does it mean to tweak to learn a polynomial G? For example, we can ask questions such as, can we find a G, a polynomial such that the L squared sum of persistence, the sum of the lengths of all the bars, is maximized across the data set of graphs? And can we find a filter function that is ideal for separating two classes of graphs in your data set in a classification problem? So we want to try and learn these parameters, and in data science, we only know how to do gradient descent. So let's see whether we can do gradient descent on this parameter space. And turns out this map, persistence homology, is generically differentiable with respect to G, whereby generically, I mean it is differentiable almost everywhere in your parameter space. And where it is not differentiable, where gradients are not defined, is measure 0. And the way to think about this is, let's say we have a path in this space of polynomials, gamma. And along this path, the order of the vertices given by the polynomials along this path is constant. And therefore, the sequence of subgraphs in the filtration is also constant. And as such, no new intervals are created and no new existing intervals vanish in this sequence, in this filtration. And therefore, what really happens when you move along this parameter space, this path in parameter space, is that the endpoints of your intervals vary smoothly. And therefore, you could define directional derivatives, and you could define tangent spaces and so on, as you would with a normal manifold. And the caveat here is this only holds along in pieces or strata of parameter space where the induced vertex order is constant, and gradients might change violently when you jump, when you do cross these, when you jump from pieces where the orders are constant to another piece where the orders are different. So the spectral wavelets are good parameterization. So what does that mean as a question? So let's say we want to solve this task. We want to find an ordered 10 polynomial for a fixed data set that maximizes the total persistence. So is it sufficiently expressive, i.e., when we change our polynomial, does it actually change this number, this sum of persistence? Does gradient descent give us something that's locally optimal? I mean, there are theoretical issues with how gradients change when we jump across strata. And can this generalize to unseen data so that G eyes open and G eyes closed be observed and hitherto unobserved data? And if we learn parameters on G eyes open, does the polynomial G star maximize the sum of persistence on unseen data G eyes shut? So we do our standard trick in data science where we do a tenfold way, tenfold cross-validation. We have a full data set and we split them up into 10 random portions. And then we look at 90% of those random portions and we solve our problem on that 90%. We don't see the pink stuff. That's a test set. And then we evaluate this on the test set. And then we just shuffle the test set around. And we repeat this for 9 extra random partitions. And we get 100 experiments. And we could get some statistics out of these 100 experiments. And what we want to see is as we ascend along this gradient of TB2 with respect to G, we want to increase TB2 for both the seen data and the unseen data. So these are some data sets we looked at. The first 2 are molecular data sets. And the last one are ego networks for movies, where each node is an actor. So this is for the first molecular data set. And I can't really do this in the live presentation, but no, if I'm sharing screen, I can actually zoom in. So one benefit of doing this on Zoom. But so the x-axis is the number of gradient descent steps, and the y-axis is the TV2 value. And for this data set, the test and train do matter very well. So it has some generalization properties, and the error bars are fairly constrained. And this panel shows how the Chebyshev coefficients evolve. And this graph shows the actual G of lambda polynomial. And the purple ones are the ones early in the filtration. And the yellow curves correspond to the G lambda learned towards the end of the gradient descent. And we repeat this for another data set for COX2, and then the molecular one, again, shows excellent agreement between test and train. For the ego data set, we do see a bigger variance, but I mean, that data set is more variable because that's the third column here. And as you can see, there's a huge difference between the graphs in the data set. So we're not surprised to see a variance. So to conclude, we have this pipeline which takes graphs and naked graphs, filter them, and we take them to space of diagrams. And we've shown some experimental evidence towards that these are expressive parametrizations. Changing these polynomials do produce a pronounced change in the functions of these barcodes. And we can optimize these polynomials. And these learned polynomials do generalize to unseen data. And this is ongoing work. So we are considering other graph linear operators, such as non-backtracking walk matrices. And there's some serious theoretical questions when we think about gradient descent and what happens when we cross from one stratum to another, whether we could design good algorithms to control that behavior, and how to make existing data science, existing neural network architectures work well with persistence diagrams that change all the time, because we do observe in some experiments that some of these perturbations to persistence diagrams do destabilize a perfectly normal neural network architecture that passes vectorizations of persistence diagrams. So I'll conclude on that point because I've run out of time, but I'll invite you to ask some questions.
All right, that's virtual claps for Ambrose. Thank you so much for a great talk. And now for questions, we're going to encourage you to ask your questions to Ambrose by typing them into the chat, and then Mason will be moderating these questions. So what we hope to do is that if you type in your question, then Mason will call on you, and then at that point, once you're called on, you can unmute and then ask your question. So I'll turn it over to Mason for moderation.
Okay, yeah. So ping me privately if you have a question, and then I'll call on you. I do not see any text.
So I have one that was sent to me.
Oh, you do? Okay. Go ahead.
So maybe I can go ahead and I see this is a question from Bibas Adakari. Why don't you go ahead and unmute yourself and ask your question to Ambrose?
I can try to find.
Yeah, so it shows unmuted, but we're not hearing anything. Well, maybe I can ask the question by proxy, which is that are the vertex sets of GI the same for all I? And what about weighted graphs?
So no, the way, yeah, so the huge challenge is, you potentially have a data set of graphs where you don't share a vertex set, and from graph to graph you get different numbers of vertices. And so the way we bypass that is just we went to the spectral domain and just operated on the spectral domain. And the second question, whether this works on weighted graphs, I haven't looked at weighted graph datasets, but I presume that you could just take your normalized Laplacian and define a similar matrix for weighted graphs.
And they say thank you. Just wanted to pass that on.
Thank you.
We maybe have time for one more question. Do you see any others on your end, Mason?
No, I don't see any on my end.
All right, in that case, let's all thank Ambrose again, and we'll get set up for our next speaker.